Hello students, in this particular video I'll be discussing about the factors that affect the chemical shift. We'll take up all the factors one by one. The first factor that affects the chemical shift is the electronegativity. The electronegativity of the substituents that are attached to the carbon atom, because of their electron withdrawing effects, they reduce the they reduce the valence electron density around the protons attached to that particular carbon. So when we are discussing the proton NMR in particular, in order to find out the effect of substituents on the electron density over this particular hydrogen atom, the effect of electronegative substituents plays a very crucial role. And these electronegative substituents actually, because they are highly electronegative, they withdraw electron towards themselves, and by this process they simply reduce the electron density across the proton, and thus the proton experiences the loss of electron density over itself. These electrons usually shield the proton from the applied magnetic field. The electrons that are surrounding the proton, they usually shield these particular protons from the applied magnetic field. So when we have an electronegative substituent over this carbon which is attached to a proton, if there is an electronegative substituent over the carbon, so what it does is it simply reduces the electron density across the proton, and since the electrons usually shield the proton from the applied magnetic field, if there is loss or reduction in the electron cloud density over the proton, they usually get de-shielded. So the greater the electronegativity of the substituents, the more de-shielded the proton is, and hence the greater is the chemical shift of those particular protons. So if we have more electronegative effect of the substituent over the carbon to which the proton is attached, that proton is particularly de-shielded to a larger extent, depending on the electronegativity of the atom that is attached to that particular carbon, and hence the greater is the chemical shift which we usually observe for those particular protons. So this is an image where we see there is a proton which is being covered by the electron cloud density. Since these electrons are assumed to be spinning, and anything that has a charge and a spin, they themselves produce a magnetic field, and this is the direction in which there is the magnetic field which is generated by the spinning electrons, and this secondary magnetic field is usually opposing the external magnetic field, which is B naught, which is having a different direction when compared to the direction or the secondary magnetic field direction which is generated by the electron spin. So we call this particular effect as diamagnetic anisotropy. So if the induced magnetic field is opposing the external magnetic field, we call that particular thing as diamagnetic anisotropy, and the diamagnetic shielding of the nucleus is caused by the circulation of valence electrons. Okay. So this is a chart where it shows the dependence of chemical shift of this particular general molecule, which is CH3X, on the element X. If X is an electronegative atom, or the electronegative atom, so how it actually influences this particular compound, that is CH3X. So we have various different molecules with CH3 in common, but the X is varying. You can see it is fluorine, OH, Cl, Br, I, etc. And you can see the element X, which is the electronegative element in all of these cases, and the electronegativity of this X is increasing from silane to methyl, methane, or this particular iodine, bromine, so on and so forth up till fluorine. If you see, fluorine is highly electronegative when compared to this silane molecule. So with the increasing electronegativity, the chemical shift values will also, if you see, the chemical shift values are acquiring the higher numbers compared to the silane and compared to this fluoromethane. If you see the fluoromethane, the fluorine is highly electronegative. That's why it is highly deshielding this particular set of protons, or the methyl protons. And usually these protons appear at the delta value 4.26. This is because of the electronegative effect of this particular fluorine over this set of protons. Similarly, we can see the electronegative effect of this oxygen over this methyl protons, where the electronegativity of oxygen is a bit lesser compared to the fluorine. That's why they appear at 3.40 delta values. Similarly, as we as we can see, there is a reduction in the electronegativity of these particular elements, and that's how the delta values are going towards 0. Okay, so that is how the chemical shift is dependent on the electronegativity of the atoms which are attached to that particular carbon, which is C in this particular case. So the substituent effects, I have highlighted all these hydrogens here. If it is more electronegative groups that have been added to this particular carbon, you can see there are 3 chlorines. Since the chlorine is electronegative with the electronegativity of 3.1, since there are 3 chlorine molecules, the delta values is shifting towards much deshaded region, that is 7.27. So the methyl protons of this trichloromethane usually appear at 7.27. Similarly, there is one less chlorine in this particular molecule compared to this, so the delta value has reduced. Similarly, the delta value has reduced in all these subsequent cases. So this is how the effect of electronegative substituents plays a crucial role on the electronegativity of a given element. So with this, I will end with the electronegativity in this particular video. Thank you very much.